So, now we are considering some external noise which is incident from the left hand side, and altogether we want to express this system by some equivalent noise temperature. Then how to calculate it? So, we have a two port network which is providing some internal noise, and it is also connected to some external source of noise which can be given by T external. So, in that case, then the total noise power at the output Ns, this is equal to K T external by L, this is for the contribution from left hand side, plus T physical into 1 by 1 minus L, whatever we have seen. We can represent it by some effective noise temperature Ts, K Ts. So, Ns, this is equal to K Ts. Now, consider one antenna. So, here you can see here. So, Ns, it is equal to K into Ts. Now, consider one antenna which is connected to a transmitter. Now, antenna, it will have some efficiency. Let us say antenna efficiency is given as 90%. Then if any power we feed to antenna, it will be attenuated by antenna, and this value it can be given by that 90% if we convert it to fraction 0.9, or we can say L, loss of the antenna due to antenna, this is 1 by rho or 1 by 0.9. Then T physical is the antenna temperature, let us say. So, this is the physical temperature of the antenna, and T external is the noise temperature of the transmitter just before antenna. So, in that case we can calculate then what the noise power available from this antenna and source, which can be given by KTS. Let us consider a receiver now, and we are going to calculate the overall receiver noise temperature. So, what we will be doing, let us first consider one amplifier, a two port network again. So, the amplification factor, it is given by GA, it is sometimes called the available gain, and TE, it is its effective noise temperature. Now, it is connected to some external resistance which is given by RL at the right hand side, and left hand side it is connected to a source of internal resistance RS, and if the source power is 0, in that case the power which is incident from left hand side, it is only the noise power. Also, the input and output resistances, they are also given for the amplifier. Now, the noise voltage available because of the noise power generated by RS, that can be given by ES equal to square root of 4 KTR. So, maximum noise power delivered to a matched load, we are considering all matched scenario, that is Pi, this is equal to ES by twice RS whole square into RS. So, you see here what we are considering. So, RS, this is the noise source. I want to extract noise power from this source, or we can say in other way, we are connecting a resistor here. So, some noise power will be delivered to the resistor. Then we are considering what is the maximum noise power that is being delivered to this resistor, and that happens according to maximum power transfer theorem, when this R, this is equal to RS, or we can write down this is equal to RS. So, in that case, if I want to calculate Pi, this is simply I square into R, then the current component flowing through it, this is Es by twice Rs whole squared multiplied by Rs, or we can write down this is equal to Es square divided by 1 Rs is cancel out. So, 4 Rs, and this is equal to Kt, which already we have seen. Now, gain of the amplifier Ga we can express in terms of the input noise power and output noise power. So, output noise power is E naught square divided by 4 into R out, and the input noise power, this is Es square divided by 4 into Rs. So, one interesting thing, then gain, you see, for even C amplifier also, if we want to calculate the overall gain of any C amplifier, it depends on RL, but simply if I say what is the gain of a C amplifier, we do not consider RL, we take just the open circuited output voltage and then calculate what is the gain of the amplifier. Now, if you change RL, obviously the available power to RL it will change, but when we call the GA or gain of the amplifier, then we do not consider RL, but this gain it depends on the source resistor Rs. So, here also then this GA it depends on Rs, but not on RL. So, output noise power, if I want to calculate at the output terminal, let us say we are denoting it by N naught. So, that is equal to G A KTS. So, KTS, this is the incident power from left hand side, which is being multiplied by gain of the amplifier GA. In addition to this, the amplifier itself it will produce some noise, which is given by N internal. In internal, this factor we can also express in terms of the effective noise temperature, which is given Te. So, we can also write down then this is equal to Ga KTS plus N internal, this is equal to Ga K into Te, or this is equal to Ga K Ts plus Te. Let us represent it by an effective temperature Gak T naught. So, T naught, this is called the operating temperature, operating noise temperature. So, you see here, this is the amplifier, and left hand side we have a noise source connected to this amplifier, and right hand side we have a load resistor connected here. Then we calculated, we expressed already a Ga in terms of the input and output noise powers, and from that we calculated the output noise power from the device. So, output noise power, what we see that it contains some the contribution due to the external noise source, which is GAKTS. In addition to that, this amplifier itself produce some noise, which is given by GAKTE. So, altogether this effect we can represent by some operating noise temperature T naught. So, N naught, then that is equal to GAK T naught. So, T naught, TE, GA all functions of RS, and but they do not depend on RL, and in this case also we assume that the output RL is matched to this, and so it is the worst case scenario, this N naught, this is the highest available noise power from the amplifier and the noisy source. Now, let us consider several 2-port components, they are connected in cascade. So, that means what we are considering, let us say we have three amplifiers. The first one gain is given by GA1, and the effective noise temperature is given by TE1. It is followed by another amplifier for which gain is GA2, effective temperature is TE2. Again we have one more GA3, effective noise temperature TE3, and we want to calculate what is the overall noise contribution of this system. So if we know for 3, we can do it for n components in cascade. Then n internal we can write down, this is equal to, so you see this first amplifier, whatever noise it will produce, let us say that is given by n internal 1. So this n internal 1, it will be amplified by GA2, further it will be amplified by GA3, but whatever noise produced by the third component, this component is not being amplified by left hand, this GA1 or GA2. Then the total noise contribution n internal, for the first one this is GA3, GA2 into GA1, K TE1. So K TE1, this is the noise produced by the first one, and it is being amplified by all these three amplifiers. Then for the second one GA3, GA2 into K TE2, and for the third one this is GA3, K TE3. So if we represent it, this overall combination, if we contribution, if we represent it by some effective temperature, let us say TE, in that case we can write down this is equal to K, TE is the overall equivalent noise temperature, then K TE into GA3, GA2, GA1. So therefore TE, this is equal to n internal divided by K GA3, GA2, GA1. So what we are assuming, as if one resistor of equivalent noise temperature TE is connected to left of this system, and the system itself is noiseless. So that is why we are multiplying by 3 gain factors GA3, GA2 and GA1. So in terms of the individual noise temperature, we can also express it. So you just put the value of n internal, whatever we obtained in this first equation. So if we put this value here, so it becomes TE1 plus TE2 by, so remaining term is GA1 plus TE3, remaining terms GA1, GA2. For n component, if we have n number of components, simply we can extend it. So it will become for nth term TEN, and below we have G1, GA1, GA2 till GAN minus 1. So this is called the Freeze law for cascaded system. So what we see then, if we have many components in cascade connection, the contribution of noise from the first component, it is the dominant over all other. So that is why when we design any receiver, the first component is chosen to have which will have minimum contribution of noise. So that is why we used a low noise amplifier typically, which will provide very low noise, and after that whatever components we are having, their contribution is smaller compared to the first component. So now let us consider a receiver, it is modeled by a constant gain G naught over a band Bn. We are introducing now some bandwidth given by Bn. Then the receiver input power is given by Ps, and it receives a noise power Pn from the antenna. Then considering matched scenario, so always by default we will be considering matched scenario. So whatever power is coming from left hand side, so it is being absorbed to right hand side, half of that absorbed in the load. So then SNR at the output of the receiver, that is equal to, you see this is G naught, SNR is signal to noise ratio. So signal at left hand side is Ps, it is being multiplied by G naught. So at output signal, available signal power is G naught into Ps. And what is the output noise power? So left hand side we have received Pn noise, it is being amplified by G naught times by the receiver chain, plus we have some internal noise contribution because of the receiver over bandwidth Bn. So Bn multiplied by n internal, and it can be given by equal to SNR at the input divided by 1 plus Bn internal divided by G naught Pn. How we come here? Simply you divide both numerator and denominator by G naught Pn. So then it the top one, it becomes Ps by Pn, which is SNR at the input. So this equation is called a radar equation for receiver. It's one important quantity parameter. Now considering available power gain Ga and this above definition, we can also express SNR at the output. So in terms of operating temperature, this is equal to Ga into Ps divided by Ga K T naught Pn. So this is the operating temperature, and simply then this is equal to Ps by K T naught Pn. So you recall this T naught is the operating temperature. Now noise bandwidth. So what if we are many time calling noise bandwidth Bn, and we are using it to calculate the overall noise power, then what value should we take for Bn for any given channel? Let's say we are using a channel bandwidth 1 gigahertz. So should we take simply Bn equal to 1 gigahertz? So whatever definition or the significance of Bn till now we have used is, it is like one simple window function which has some value over the given bandwidth, and out of this band it has 0 value, but it is not the practical scenario. So let us consider any practical case. So in this expression, when we use some value of Bn, so that means, let's say we are considering the ideal scenario. This is the 1 gigahertz channel bandwidth, it's given Bn, and then we model it by a constant gain Ga when we talk about the gain of the amplifier or gain of the receiver G naught, whatever, and out of this band this Ga is exactly 0. But for any practical system, consider any band pass filter or anything, so for that it's not constant, but it becomes a function of frequency, and we have contribution due to, you see, other frequency components. So it will vary. So gain Ga, it's a function of frequency, and bandwidth Bn, then what value we should take for this type of practical scenario? So what we do here, there is a way for calculation. For a real system, obviously it will be defined by its transfer function h, which is a function of j omega, and the corresponding temperature, which previously we consider constant over the frequency, but practically it should be a function of frequency. Then actual output noise power, we should consider all the frequency bands starting from 0 to infinity, and we integrate it over 0 to infinity h j omega square k t naught df. Now, if t naught is constant over the band, and let us say mid band gain is given by Ga equal to h j omega naught square, in that case, so we are assuming t naught is constant, otherwise it is becoming complicated for simplification this assumption. So, Bn, this is equal to then total noise power Pn divided by k t naught Ga, or 0 to infinity this integration value divided by h j omega naught whole square. So, from this expression we can calculate Bn value, but even then you see here we considered t naught is constant over this given bandwidth. Next, noise factor. So, total noise contribution, it can be calculated in terms of noise temperature. Also, sometimes another parameter is used to quantify the noise contribution, that is called noise figure. We can calculate it for any given two port devices. So, usually if it is a lossy device with some insertion loss, let us say L in dB, then noise figure in dB, it is simply becomes equal to L. If you buy any active components like amplifier or some active mixer, usually the noise figure value will be written or given by the manufacturer. It can be also measured in lab by using in lab experiment by using spectrum analyzer and standard noise source values, or VNA, vector network analyzers. So, in general, then what is, first let us define noise factor of a two port network. Noise factor F, this is the ratio of signal to noise ratio at the input terminal divided by signal to noise ratio at the output terminal. So, SNR at the input divided by SNR at the output. Now, signal to noise ratio obviously is better at left hand side compared to right hand side at the output. Why? Because at the output side we have additional noise generated by the component itself. So, that is why F, this is always greater than 1. If we express it in dB, we call it noise figure, and that is always a positive quantity. So, for a given system, then already we did it, let me express mathematically. So, then the noise factor F, this is equal to SNR at the input terminal divided by SNR at the output terminal. So, at the input terminal, let us say the power already whatever we assumed in previous example, PS is the incident power, and let us say Ni is the incident noise from left hand side. We are considering per unit hertz. So, this is the SNR at the input side. Now, we can calculate SNR at the output side. So, then the available power is the amplification factor Ga multiplied by PS divided by total noise. Total noise is some noise internally generated inside the two port device plus the contribution from left hand side, which is Ga into Ni. So, this is equal to then Ga k T naught plus N internal divided by Ga k T naught. Now, it is a function of temperature. You see, then what value we should take for T naught. So, if the noise from my left hand side it changes, obviously this value will change. So then if we buy, let us say, one amplifier from market, some noise figure or noise factor is given with that, then what it denotes, because it becomes a function of input noise. So usually a standard temperature is considered to calculate noise factor and hence noise figure, that is 290 Kelvin. So if I do not consider simply actual scenario, practical scenario, by noise factor we means the noise contributed by the components, it has been calculated at a given T naught equal to 290 Kelvin. So from this, then you see, if I put N internal, that is given by GAKTE, T is the equivalent noise temperature. So then it becomes simply 1 plus TE by T naught. So TE, this is the effective noise temperature of the two port device itself. T naught, this is for standard calculation, we will consider 290 Kelvin. Then we can express TE also in terms of F. So TE equal to F minus 1 into T naught. This is another important expression. So if F is given, we can calculate what is the effective noise temperature TE. If TE is given, we can calculate what is the noise factor F. So they are related by this important relationship. Now this noise factor depends on source impedance and operating frequency, obviously. If we have a lossy network, as I discussed, it will provide you some insertion loss or power will be attenuated by the two port network. If the loss is given by L, then simply its noise factor is equal to L. And now we are considering a different scenario. Let us say this source temperature, it is not T naught, it is given by Ts, whatever we considered in the previous case. Okay, so let us take a break, then we will consider a practical scenario with a given temperature Ts.